So in the previous segment, we talked about how the pressure was the same on the left and the right, that the force and pressure was less up top than the bottom, and that's what causes items to have a force. We realize that this force is called the buoyant force, FB, and so this upward force is the force exerted on an object immersed in fluid. Okay? Force buoyance is equal to the weight of the displaced fluid. Okay? We learned that the force buoyancy was density, which is rho, times gravity times the volume. And it was the density of the fluid we were in, the volume of the object, and the gravity. But the volume of the object is also the volume of the liquid we've pushed out of the way, right? And so what is density times volume? Mass, yeah. Density is times volume is mass. Well, that makes sense. Force buoyancy is just the mg of the water. It's just the force of gravity of the missing water. Think about that for a second. If I have a ocean, and in the ocean there is a boat, the only thing that really is pushing the water out of the way is the mass of the whole boat. It could be much more boat than just that. I mean, you have what, a whole ship built on top of this, maybe some smokestacks. But in terms of the boat, this green section is the water that's been pushed out of the way of the boat. And the water that's pushed out of the way of the boat will equal the mass of the boat itself. The amount of water that's missing is the mass of the boat. So the buoyant force is the displaced fluid. The apparent loss of weight of an object of the fluid is equal to the weight of the fluid displaced. That's the buoyant force. Buoyant force by the object. So the apparent force of gravity, wait. If I drop a tennis ball here, we know it drops at and accelerates at about 9.8 meters per second. Is that true if I drop, let's say, a marble here? But what happens if I drop a marble not in the air and through the air, but through water? It slows down. And so there is what? The gravity apparent would be made up of what two parts? So the down is still gravity. What's the up? Yep, the buoyant force. Good.
So then things have a natural buoyancy in air.
Yeah, there's the buoyancy of air. We tend to neglect that when we're talking about 9.8 because things cut through air readily. Air is also compressible. It gets out of the way. But when we get to the calculus of it, it would be also the fact that air slows it down the faster it's moving. And so to get there, we're not ready for that until we do the calculus of it. But the apparent weight is all the true weight minus the buoyant force. This is when we worry about down being negative. But when we talk about net forces, that's because the net force is the force of buoyancy, that's the upwards, minus gravity. And I'm just switching around my signs to talk about it in terms of net force. This means when we look at a weight hanging into the water, we have this mystery weight with what hanging down? What's pulling everything down? So mass times gravity is the force of gravity. But what else is happening to it? For it to be suspended in the liquid, we have the tension in the rope and buoyancy. So for this to not be sinking, there's tension in the rope and buoyancy. And depending on the volume of that object and the density of that object, it could be more buoyancy than tension, more tension than buoyancy. But overall, that's the free body diagram is going to have those three forces. And if it was a scale, that scale would measure just the tension pulling down on the hook, right? Which would match the tension pulling up. So you could actually measure the leftover force because gravity's pulling down, buoyancy's pulling up. And so if it's attached to the scale is literally just measuring the apparent gravity of it. Okay. If the force buoyancy is less than the weight of the object itself, the object has a net downward force and will sink. Let me just rephrase this for you. If your object's density overcomes water, it sinks. Right? In terms of density. If the object floats, then the buoyancy balances it is balancing its weight. And we say it balances the weight because I think of this boat up here. This boat only sinks as much as it needs to balance it because you have to have equal forces. If you take a volleyball and try to shove it underwater, you know that if the buoyancy overcomes the weight, we have a net what? Upward what? Yeah, an upward force, and it will accelerate. Accelerate upward. Used to be a thing where we would try to get a volleyball as low as we could in the pool, and then we just let it go and see it shoot out of the water with its speed.
With kickboards, like it was a thing to try and get them underwater, and they'd always shoot back.
Kickboards, the little boogie boards. Surfboards are a little too hard to get underwater because they're typically very buoyant. Right, but they're built to hold up a whole person, so you would need several people. I guess, yeah, you could try. No, yeah, okay.